Hey everyone, my name is Jan Ponte, and this is my final project for CIS 589 at the University of Michigan Dearborn. So this project is called a privacy-preserving adaptive edge facial recognition system for smart home security. I know that's quite a mouthful, so let me break it down for what that actually means over the next few minutes. The short version is, I built a facial recognition system that runs entirely on a Raspberry Pi 5 in your home using a camera module 3, and it never sends your face or video data anywhere. The intelligence stays on the device, and on top of that, it adapts in real time to changes in lighting, image quality, and CPU load, which is something most existing edge systems just don't do. I'll walk through the problem I was solving, how the system works, the code that makes it tick, and then the actual results from running it on real hardware. So why does this project exist? Let's start with that fundamental question. The starting point is that almost every popular smart home security camera system, whether it's Ring or Nest, works by streaming continuous video to the cloud, where facial recognition runs on third-party servers. So this creates three problems. The first one is privacy. Your biometric data, your face, is being sent out over the internet and stored somewhere you don't control. And this isn't a theoretical concern. In fact, in 2021, a single breach of a company called Verkada exposed live footage from over 150,000 security cameras across hospitals, schools, and prisons. One breach, 150,000 cameras, just because the data was all sitting in one place in the cloud. The second problem that comes to mind is bandwidth. A single 1080p cloud camera can consume 1 to 3 gigabytes of data per day, even when nothing is happening. Now that's a lot of upstream bandwidth to burn just watching an empty hallway or an empty front entrance or any other non-active area. Third, and this is the gap where existing edge systems don't necessarily address, is that systems try to solve the first two problems by running a fixed pipeline on device. One detector, one recognition model, and the same treatment for every frame, regardless of whether it's well lit or pitch dark, or whether the person is moving fast, standing still, or even when the CPU is running hot. This works in a demo, but this doesn't actually hold up in a real home environment. So the solution I built addresses all of these problems. The core idea is to move all the intelligence to the edge, meaning everything runs locally on the Raspberry Pi 5 in your home. Face detection, face recognition, identity matching, quality assessment, resource monitoring, all of it stays on hardware you own. The only thing that crosses into the cloud is a short text-based alert when someone the system doesn't recognize is detected. That alert, that alert is around 200 bytes, maybe even a small face thumbnail. No raw video, no biometric data. The Pi Camera 3 streams to the Pi decides, and only the decision leaves the home. On the left is the edge layer, and that's where all the work happens. The allowed person's database lives locally on disk, and the facial recognition model runs locally. And the adaptive logic I'll describe in the following slides all happens right here on the Pi. On the right is the cloud layer, and you can see how thin it is. It's just a notification relay, and if the Pi decides someone unknown is in the frame, it fires an alert through something like a push notification to your phone. That's it. The privacy guarantee is structural. Biometric data never leaves the home network because we never put it on the network in the first place. So let's talk about the full processing pipeline and how this all works. The 5 stages are that every frame goes through from the moment the camera captures it to when an alert is potentially sent. Stage 1 is the frame quality assessor. Before we do anything expensive, we score each frame on brightness, sharpness, and contrast. Based on that score, the frame gets one of 3 routing decisions: pass, enhance, or skip. I'll show the actual code for this in a couple of slides. Stage 2 is adaptive enhancement moduling. If the frame quality assessor said enhance, the frame goes through CLA-HE, which is a contrast equalization technique, plus gamma correction and some light denoising. If the frame is fine, this step is skipped entirely, so you don't need to pay the cost on frames that you don't need. Stage 3 is the tier selector, and this is where resource awareness comes in. There are 3 recognition models loaded in memory at once: fast, balanced, and accurate. A background thread monitors CPU performance, temperature, utilization, memory pressure, and inference queue depth. And the selector picks which model tier to use on this frame right now based on those signals. Stage 4 is tiered recognition. Whatever tier was selected runs the actual face recognition, generates an embedding, and compares it against the local allowed persons database using a similarity analysis. There are no cloud calls here. And stage 5 is the temporal confidence aggregator. Rather than alerting on any single frame, it accumulates evidence over a rolling 3-second window, weighing each frame's vote by its quality score from stage 1. An alert only fires when that weighted evidence consistently points to an unknown person. And then the output on the right, and then the output fires an alert or a short text notification that goes to your phone. That's the only thing that leaves the edge layer. So let's talk a little bit about the hardware. So the hardware is a Raspberry Pi 5, the 16 gigabyte variant. This one I personally picked just to compensate for any implementation inefficiencies or any code intensive processes. Camera Pi Module 3 connected via a standard CSI ribbon cable. The camera Module 3 uses a Sony IMX708 sensor, 12 megapixels, and importantly has a phase detection autofocus built in, which matters for recognition because without it you'd need to manually set focus for a fixed distance. I used the standard 75-degree field of view variant captured at 1280 by 720p at 30 frames per second. I fitted a passive heatsink and deliberately did not add a fan, so that the thermal behavior I measured reflects a realistic deployment rather than an optimized lab setup. On the software side, the implementation is about over 2,000 lines of Python code across 8 modules. The main dependencies are PyCamera 2 for camera access, OpenCV for frame processing, NumPy for the math, and SciUtil, plus DirectSys FS reads for resource monitoring. Now that PicCamera 2 note deserves a mention. One of the first challenges I hit was the obvious approach for CV2 video capture. That simply doesn't work for the camera module 3 on Raspberry Pi OS. The legacy V4L2 shim that almost every tutorial on Stack Overflow answer assumes is really no longer installed by default. So CSI cameras are exclusively libcamera managed now. So I had to build a custom camera abstraction layer that auto-detects the available camera and routes to PyCamera 2, which falls back to OpenCV's video capture only for USB webcams. I think that's the biggest warning I want to call out. It took longer than it should have to figure that out, and I thought it was worth mentioning. So let's go through some of the key code. I'll show a little bit because I don't want to bore everyone with the code. So this is the frame quality assessor. So this is the first thing that runs on every single frame before any facial recognition software happens. Or, excuse me, facial recognition actually takes place. The idea is pretty straightforward. Not every frame is worth sending through a heavy recognition model. If it's dark, blurry, or totally washed out, you're just burning CPU usage on data that you can't even make anything useful from. So the FQA scores the frame first. It computes 3 metrics: brightness, mean luminance of the grayscale frame, scored against a target band of roughly 60 to 200. Below 60 and you're in the dark. Above 200 and you're overexposed. Sharpness was the next thing that was measured. So this uses the variance of the Laplacian, excuse me if I'm not saying that correctly, which is the standard for blur detection. The Laplacian is an edge detector, and sharp images have lots of strong edges, so the variance is high. Blurry images are smooth, so the variance collapses. By contrast, the standard deviation of the histogram. So that means low standard deviation means everything is washed out to roughly the same gray area. So all these 3 were normalized to 0 to 1, or from 0 to 1, excuse me. Then combined using a geometric mean, and this is the important design choice. You can see it here: brightness plus EPS times sharpness plus EPS times contrast plus EPS, raised to the power of 1 over 3. The reason for the geometric mean over an arithmetic mean is in the comment. One bad decision tanks the score. If a frame is perfectly sharp and high contrast but completely dark, it's useless. An arithmetic mean would let the other two carry the dark component. A geometric mean doesn't. If any one factor is near 0, that product collapses. Then the routing decision, below 0.2 overall, we skip, and that's in red. Don't run recognition at all if we skip, right? So between 0.2 and 0.55, enhance, which is what's listed in the if-else, or elif condition. That sends it through the enhancement stage first. So anything above 0.55 is a pass, and that goes directly towards recognition. So a well-lit, sharp, high contrast frame pays 0 enhancement overload, and a completely dark frame gets rejected immediately without ever touching the recognition model. All right, let's move on to the next one, the resource-aware tier selector, right? So the tier selector handles the resource side of the problem. The idea is that you can't pick one recognition model and run it forever. If the CPU is under sustained load, an 80 millisecond model will start dropping frames. But if everything is fine, you want the most accurate model available. So I keep 3 models in memory simultaneously. There's fast, which is a mobile FaceNet variant targeting about 5 milliseconds. Balanced is FaceNet on mobile net v2 targeting about 25 milliseconds. Accurate is an ArcFace MobileNet variant targeting about 80 milliseconds. A background thread polls CPU performance, CPU utilization, memory pressure, and inference queue depth at every 500 milliseconds, and updates a resource state object. The select method here is a state machine. You can see the priority order. So the first check is if the CPU is above the hot threshold, 78 degrees Celsius usually, drop immediately to fast with no questions asked. The second check is the inference queue in saturating. So drop to fast because we're already falling behind. The third check is if CPU utilization is above 75%, drop to balanced. A softer downgrade for a softer pressure signal. So the upgrade path at the bottom works differently. It only upgrades after is safe has been true and a full cooldown period has taken place. That asymmetric design is intentional. Downgrades are immediate because of the cost of overshooting is high, right? So upgrades are slow because a brief, safe reading might be noise, and oscillating between tiers has real overhead since each switch flushes the model's cache on warm-up. Keep in mind that each time you switch, there's a cache warm-up that you have to pay, which can make a huge difference in performance. Now, there's an interesting point resulting from my actual 30-minute run. I actually expected the temperature thresholds to be the active trigger, but they weren't. The Pi 5 with a passive heat sink peaked at about 60 degrees Celsius, which is well below the 72 degree and warm threshold. The trigger that actually fired was the CPU at utilization rate at t equals 38.5 seconds when the CPU hit 95 seconds. So the system dropped to balance and stayed there for the remaining 29 minutes. In practice on this hardware indoors, CPU utilization is the practical adaptive trigger. The temperature thresholds are still worth having for unusual deployments. A warmer room, a smaller chassis with a heat sink, but they didn't fire up in my setup, and this system handled it correctly either way. The next portion we'll talk about is the temporal confidence aggregator, which is the last piece, and I promise I won't talk about code after this. And it's directly motivated by a real failure mode I wanted to fix. So if you alert on every frame that comes back as unknown, you'll get flooded with a lot of alerts whenever somebody walks past quickly or there's motion blur. And to keep in mind, that is a really big problem, especially when it comes to anybody walking by your frame. And you'd be sending your phone a notification for garbage data. So instead of per frame alerting, the TCA maintains a rolling 3-second window of recognition outcomes. The add method is simple: append the result and quality check, evict anything older than 3 seconds, and then check for an alert. The wait is the key part. So each frame's vote gets multiplied by its FQA quality score from stage 1 A frame that scored 0.9 on quality contributes 0.9 of a vote. A frame that scored 0.05 blurry dim contributes almost nothing. So a stretch of motion blur where the recognizer was essentially guessing barely moves the weighted share at all. In the maybe alert, right? So the case of a maybe alert, the minimum samples gate comes first. So anything fewer than 3 frames in the window returns none. This prevents a single frame from triggering anything. Then the weighted calculation, total weight is the sum of all quality scores. Unknown weight is the sum of quality scores where the result was unknown. And share is unknown over total. If that crosses over 0.55, the alert fires. There's also a 10-second window of cooldown between alerts, so you don't get repeated notification while someone is just standing there. The practical effect of this is that the system is skeptical of individual bad frames, but responsive to sustained evidence. One blurry unknown frame in a window full of clean unknown frames barely registers, but if someone unrecognizes consistently in the frame across multiple clean captures, the weighted share climbs quickly and the alert fires accurately. So let's talk about the actual results. So let me start with the pipeline performance from my 30-minute sustained load run with stressing pushing all 4 CPUs simultaneously. The four metric cards at the top tell the main story. Average end-to-end latency was about 35.65 milliseconds. My target from the project proposal was under 100 milliseconds, so that's a comfortable margin. Throughput was at least 20 frames per second throughout the entire run, which was my design target. Memory utilization held steady at 6.4%. There was no memory growth over time, which confirms that the pipeline doesn't leak. And CPU peak performance was 60 degrees Celsius, which I can come back to later. The bar chart on the left breaks down latency across 4 categories. The minimum of 2.32 milliseconds is from frames from the FQA routed to skip. Those bypass recognition entirely, which validates the abstention design as a real CPU saving mechanism. The average of 36 milliseconds is the sustained steady state. So the maximum of 178 milliseconds is the brief, accurate tier window in the first 38 seconds before the tier selector downgraded. On the right is the tier selector behavior log. The system started at balance, upgraded to accurate at 5.5 seconds once the cooldown elapsed and the resources were saved. Then it downgraded back to balance at 38.5 seconds when the CPU hit 95%, and it stayed at balance for the remaining 29 minutes and 21 seconds. That's clean deterministic behavior. And that last line, the temperature thresholds, never fired. It peaked at about 60 degrees against the 72 degree warm limit. So on a Pi 5 with a passive heat sink and a normal indoor room, CPU utilization rate is the trigger that actually does the work. The temperature thresholds remain valuable as a safety net for unusual deployments, but they didn't activate here. So this slide shows the recognition accuracy across 6 capture conditions I tested. And I want to be upfront about what these numbers mean and what caused them. The standout result is the occluded condition at 98.3% for both pipelines. That's the strongest result in the data set, and it proves the end-to-end pipeline camera 2Pi recognition 2 database works correctly when the recognition backend can do its actual job. Most of the other conditions show 0% for both pipelines, and the root cause is on the banner at the bottom. The simulated embedding model I used. Rather than integrate real TF Lite facial recognition models during the project window, I used a deterministic structural hash stand-in that produced embeddings from a down-stamped quantized version of the face crop. On synthetic test data, that works fine. On real Pi camera module 3 footage, the per frame variation from autofocus adjustments, sensor noise, and natural pose shifts causes the same person structural hash to differ between enrollment and evaluation frames. So the matcher returns unknown almost every time. And this is the known limit or limitation of the simulated backend, not a property of the FQA, the tier selector, or the TCA. The fix is pretty straightforward. Replace one method in recognition.py with a TF Lite interpreter call to a real model like mobile FaceNet. The rest of the pipeline will stay exactly the same. There's one result that's worth explaining separately, and that's blurry, where adaptive was slightly worse than baseline, 25% versus 40%. And what I think happened here was that CLHE enhancement modified the pixel structure of the blurry frames in a way that moved the structural hash further from the enrollment hash rather than closer. So with a real learned embedding model, enhancement should improve recognition. Learned models are trained to be robust to exactly this kind of pre-processing. But again, this is an area for future built research, and I can't verify that without actually doing a model swap. So this chart answers a question I had while building this system. Does the FQA's quality score actually predict recognition success? If it does, then the FQA is pulling its weight regardless of which recognition model sits behind it. If it doesn't, then it's really just overhead. So the x-axis is the FQA's overall quality score, binned into ranges. So the y-axis on the left, the blue line, is recognition accuracy for frames in that bin. The bars are frame counts, how many frames fell into each bin, and the result is clear in the populated bins. Frames with quality scores in the 0 to 0.3 range produce especially zero correct recognitions. Frames in the 0.5 to 0.7 range produce correct recognitions, 25 to 35% of the time. The relationship is monotonic, so higher quality score, better recognition outcome across the dense part of this histogram. This direct evidence that the FQA is doing useful work is pretty evident. A downstream recognition stage that prioritizes high quality frames, which is exactly what the enhance and skip routing decisions do, will perform better than one that processes all frames equally. And this relationship should hold even more strongly with a real recognition backend, where absolute accuracy numbers across all bins will be much higher. The monotonic shape is a property of the quality assessment logic, not of the simulated backend. So again, just to reiterate, this is more so a laying of the foundation, and the results show that there's a lot of promise in this particular method, especially when it comes to edge computing for facial recognition. So this is the 4-panel trace from my 30-minute sustained load run with stressing running on the parallel shell. This is the most complete picture of how the system behaves in practice over time. So let's start with FPS at the top. You can see it starts very high at the first few seconds, which is frames being rapidly skipped by the FQA before the camera scene even stabilizes. Then it settles into the 20 to 30 frames per second sustained range you see for the rest of the run. The 10 frame per second target line is the dashed line near the bottom, and the system stays well clear of that throughput. The tiered panel in the second row shows the two transitions I described earlier. A brief moment at accurate, then drop to balance at around 38 seconds, then flat for the remaining 29 minutes. You can see exactly where the CPU utilization trigger fired. The temperature panel is the orange line. So it climbs from about 49 degrees at startup to around 58 to 60 degrees during the sustained load, and it holds there. The dashed line at 78 degrees is the hot threshold, and you can see the actual temperature never came close to it. The Pi 5 has genuinely really good thermal performance under this kind of load. And the FQA's quality score at the bottom is the green line. This reflects what the camera was looking at, a static indoor scene without a person in frame, with modest background lighting and low sharpness on the background texture. That produces FQA scores consistently in the 0.2 to 0.5 range, which is why 83% of frames went through the enhancement path. If a person had been in frame under good lighting, you'd expect to see spikes of about towards 0.6 and 0.7 when a clean face is visible. So the key takeaway from these results is the system ran for about 30 minutes under sustained CPU pressure with no crashes, no memory growth, no thermal shutdown, and consistent throughput above design target. And that adaptive behavior worked really well. So let's talk a little bit about the facial recognition and actions. So this slide, I'll show some actual screenshots from the system running live on the Pi. So the 6 frames here came from my capture sessions using the capture.py script I built. Each one represents a different condition. A clean enrolled resident under good lighting, the same person under dim conditions, partial occlusion, and an unknown person, which did trigger an alert. A blurred frame where the FQA correctly skipped recognition entirely, and a frame that went through the CLA-HE enhancement path before being recognized. So if you look at the demo.py overlay in these screenshots, you can see the live diagnostic information that the system was displaying. Unfortunately, it only came through for the enrolled resident, the unknown person alert, and the enhanced frame. but you can see how it recognized me. It didn't recognize a picture of someone else that I pulled up. And then it also showed the enhanced version under dim light conditions, as well as the CLHE applied. Um, the other photos are showing conditions like dim lighting, occluded, so I wore sunglasses, and the motion blur where I kept rotating my head side to side. Overall, these images were pretty compelling, and it showed just how good the results were. All right, so let me wrap up with what was accomplished and where this goes next. So on the left, this is what actually works. The system ran for 30 minutes under sustained CPU stress without a single crash or memory issue. It held at about 20 frames per second the entire time, and the average latency was 35.65 milliseconds, which is well under the 100 millisecond target. The sear selector responded correctly to CPU pressure, which is making exactly the transitions you'd want. The FQA correctly abstained on every single frame captured in dim lighting, which is pretty much the right call. The FQA quality score monotonically predicts recognition success. The occluded condition hit 98.3% accuracy, proving end-to-end pipeline correctness. And all 16 of the unit tests that I wrote on the Pi 5 passed. On the right, you'll see the next steps, and I listed them in priority order. So number one, and by far the most impactful, swap the simulated embedding backend for a real facial recognition model. You can either use mobile FaceNet, or ArcFace, and they're all pre-trained, quantized, and Pi 5 compatible. That's a one method change in recognition.py. Everything else in the pipeline would remain the same. And this is the single change that most likely would make the per condition accuracy numbers on the earlier side go from 0 to something competitive with cloud-based systems, all while keeping the adaptive behavior and privacy guarantees. And then after that, replace the HAR cascade with a modern detector like BlazeFlash for better detection in challenging scenes, and online enrollment refinement using TCA's high confidence known frames over time. Measure power draw via GPIO, and add anti-spoofing for production and deployment. And the bottom line for all of this is that the architecture works. The privacy guarantees are structural. Biometric data never leaves the home. The adaptive behavior is real and measurable, and the gap between where this is now and a deployable system is one method swap in a file. And that's pretty straightforward. So I really want to thank you for following along with me and understanding the entirety of my project, and thank you for watching.